In this lecture, I show that the vector fields with which we built the sub-Riemannian metric on Heisenberg group are indeed the left-invariant translations of the canonical vectors at the origin in R3. For this, I want to give a quick review of what Lie groups are and what they do. And again, I refer to Professor Ledone's videos for a thorough introduction to the topic, or pick up any book that has a Lie group chapter in them. If we are looking at a general manifold, a Riemannian manifold, it has a smooth structure. You could even imagine that it has a metric. There is no way you can compare vectors from one tangent space, Txm, to vectors in a different tangent space, Tym. As soon as your base point is different, there is no way to say this one vector corresponds to that other one. There is just no canonical way, even on a simple example as the sphere. However, if your manifold happens to also have a group structure where multiplication and inverse are smooth operations, then if you give me x and give me a different point y, there is a unique, a canonical operator that maps x to y. Take z to be y times x minus, so this is an element in the Lie group M. Now the operation of left translation by z from M to M is smooth because of assumption that all multiplications are smooth. And we see that Lz takes the point x to y. Now if we have a smooth map, it has a derivative, a differential, which goes from tangent space in the origin to the tangent space of the action of that function at x, which is y, of the target manifold, which again here is M. So this is a linear map from tangent space Txm to Tym. Therefore, we can say that a vector v in Txm is same as the vector that it maps to under the differential dlz. So this is a choice we make, of course. We could also work with right translations, but this is at least one way of saying which vector in the other tangent space is uniquely corresponding to the one here. Also, this map is invertible, and this gives an isomorphism. So if there is a group operation on a Riemannian manifold that is smooth, we can always do this. This we see in Rn already, but under the disguise of coordinate systems and so much notation involved in Rn that we just casually say vector v here is the same as the one here. Well, basically they point in the same direction and they have the same coordinates. So we are too much coordinate independent in Rn, and it hides this reality that this identification means that the plus operation, so here from Rn to Rn, and you fix a point and you say, okay, x maps to x plus z. So this is a smooth operator. You take derivative and you apply it to the vector at x, and it gives us a vector at y. In this viewpoint, we see that this is a much deeper notion because it's independent of the choice of coordinate system. It actually is intrinsic. It comes from the geometry of Rn rather than an artificial choice of vector fields and writing v as, say, AB, and then here seeing that it's again AB or something. And this is the Lie group is a generalization of this notion that we can identify vectors everywhere. Of course, vectors are not the only things that we can in a such canonical way identify from one point to another. You can move forward, say a metric. If you start at a metric and an inner product on TXM, you can transfer it by this left translations to all of the other tangent spaces, and you can build a Riemannian metric that is invariant under these translations. And again, I don't want to get into the theory of and details of what manifolds and Lie groups are. Now back to the case of Heisenberg group. We just in the past lecture introduced the product that is non-abelian and we equip it with. So it's R3 with this multiplication, which is almost the same as R3 with the abelian plus operation, except that in the third coordinate we have this extra twist to it, which is also non-abelian. So this is the group structure, but previously we've seen that H1 was equipped with R3 with its usual smooth structure. So that's the manifold underlying the thing. And we had built a metric by considering those vectors whose velocities lied in the span of two very special vectors. And they were partial x minus 2y partial t. Y was partial y plus 2x partial t. Now, to connect these two structures, I want to show by calculating simply that x and y are simply, and also this explains who would come up with this formula, who would have guessed it. No one guessed it. It's just simply a left invariant under this operation. Translation of partial x and partial y at the origin. I want to change my notation here and say y naught and x naught. So that is these vectors at the point x naught, y naught, and t naught are given by these, and the symbols partial, these are kind of cheating and borrowing the global coordinate system of R3. So from the group structure, these are nothing. They don't exist really. So they come from once we equip R3 or H1 with the standard chart or global coordinate system. What is intrinsic and truly intrinsic to this geometry are the vectors x and y. So if we actually were living, we were creatures whose perception was Heisenberg group structure, what we would be seeing in the Heisenberg group, rather than seeing a vector that changes from here to here, this vector x, we would see what we see in Euclidean geometry. This is the same vector. So although from our Euclidean viewpoint this x changes size, here it's like that, and then it changes size, or so from our Euclidean viewpoint these become really different vectors. From the intrinsic geometry of the Lie group, all of them are the same, just like how V in Euclidean space we kind of have a constant vector field. So in the Lie group structure given by this product, rather than the R3 with the plus, this is the picture that we have, that all of them are just the same. But when you write it in the coordinate system coming from R3, standard R3, that's why their shape changes from one point to another. So I hope I made it clear. So something here is intrinsic versus something that is simply because how we write down things in a coordinate system, in a in an arbitrary coordinate system, honestly, that has no respect for the group multiplication. Anyway, so let me prove this claim then. How do I know that if I take partial x at the origin and left invariant and translate it by left multiplication to the point x naught, y naught, v naught, it will end up being this. So let's just follow the definitions. Let me clean up a little bit room here. So I have to calculate the differential of this operator. So left multiplication into x naught, y naught, and t naught is given up here. This is the formula. So it takes x, y, t to this. And the smooth structure is the standard R3 smooth structure. So the derivative of this, which will be a 3 by 3 matrix, will be, okay, in the first coordinate here, partial with respect to x is just 1, partial with respect to y is 0, partial with respect to t is 0. So this will be the differential operator, the linear operator, which maps tangent space at 0, 0, 0 of h1 to tangent space at x naught, y naught, t naught. Let me actually switch this to R3 because the underlying manifold and the smooth structure on it is R3. In the second coordinate, we see 0, 1, and 0. In the third coordinate, the derivative with respect to x is 2y naught. Derivative with respect to y is negative 2x naught, and derivative with respect to t is 1. So this is the linear operator that is between the tangent spaces given here. And now we say, okay, what does this operator do to the vector partial x? So that will be this matrix acting on 1, 0, 0. And that is just the first column, 1, 0, 2, y naught. If you multiply a matrix into this, this means 1 times first column, 0 times second column, 0 times third column. That's how I multiply into vector. And this, in other words, is partial x plus 2y naught partial t, which, surprise, is x at y naught t naught from before. So yes, x is the translation of that. If you just simply apply it to, actually I have dropped, so dl at x naught, y naught, t naught applied to partial x. And now if you do the same similar argument with partial y, you multiply into the second vector, and so it will be partial y minus 2x naught partial t, and that is y at x naught, y naught, t naught. So we have gone about this, by the way, in a little bit weird way. We did everything sub-Riemannian metric with these vectors without explaining where they came from. We took it for granted that someone tells us these are special vectors. Now we're showing that they are indeed left invariant. So the actual way would be you start with the multiplication and then look at the translations and write down these vectors. And you can also verify that the left invariant translation of the vertical direction, that is partial t, is always itself. So that just this coincides with the R3 abelian translations. Another feature of this matrix, an important one, is that its determinant is equal to 1, and the consequence is that the measure, the Euclidean Lebesgue measure, is left invariant under this, and that makes it the Haar measure. It's a consequence of the change of variables formula, that if you have a set and you look at the image of the set under this map L, x naught, y naught, t naught, because this determinant is equal to 1 everywhere, the measure of the image, the L3 measure of the image, is the same as what you started with. That's why L3 ends up being left invariant, so up to a constant, the unique Haar measure of Heisenberg group. So that explains the story of where these vectors come from and how one finds them. I had this very old lecture from a couple of years ago, in fact, not part of this series, where I even explain why one, where I explain how one even constructs this one to begin with, because this multiplication itself is not that intuitive, and there I use this Campbell-Hausdorff formula and explain how you start with a Lie algebra, and simply by requiring that I want the bracket of two vectors to be the third one on R3, you can build the multiplication. You can really calculate and say the multiplication has to be this. But I think this is good enough for one lecture, explaining why the left invariant vector fields are the x, y that we had previously worked with. And this combines the previous discussion of sub-Riemannian metric of Heisenberg group with now the Lie group structure of it. I will have some more consequences of this in future lectures. Thanks for watching and have a good day.